In the first part of this video lecture, we defined finite cuboids, defined what are the Borel sets on the Euclidean space of d dimensions Rd. Then we defined the Lebesgue measure on Rd and stated a theorem claiming its existence and uniqueness. Now in the second part, we'll discuss a convenient algebra of sets of Rd, define a pre-measure on that algebra, because then, as usual, Carathéodory extension theorem will give us the existence and uniqueness of the Lebesgue measure, and then we briefly discuss some examples that will help us have a grasp on how to understand Lebesgue measure in high dimensions. As a brief reminder, finite cuboids in this module we define as the Cartesian product of finite intervals, left open, right closed intervals. In 2 dimensions it will be squares like this, in 3 dimensions it will be cuboids like this, in higher dimensions we use our imagination. And the Lebesgue measure is the unique measure that assigns to each cuboid the product of its dimensions. We now move on to defining an algebra on the subsets of Rd, and on that algebra we'll define a pre-measure. Before defining the algebra, we introduce the concept of cuboids. So the difference between cuboids and finite cuboids is that finite cuboids have the projection in each direction like this, and cuboids in general can have infinite projections which are infinite either in one direction or in the other direction. In 2 dimensions, cuboids can have many different shapes. This will be a finite cuboid, but all these other 3 sets here are also cuboids, which are just a generalization of the notion of rectangle in 2 dimensions. Now in 3 dimensions we see that there are many more possibilities. I'm just showing here a few of them. Here is a pillar. A pillar is infinite in one direction, but then it is just a rectangle in the plane perpendicular to it. Or we can also have slabs. Here's a slab. It is infinite in 2 directions. This direction and this direction is infinite. And in the first direction, it is just an interval. Open on the left, closed on the right. And why do we need to talk about cuboids, not just finite cuboids? Well, the answer is simple. If we want to have more structure in our family of sets, and we want that structure to be that of an algebra, how can we take the complement of a cuboid or rectangle? Well, the complement of a cuboid, a finite cuboid, will be this object which is infinite in 2 directions. It's infinite in that way and infinite in that way. And how does it help? Can it be any useful? Well, we can write this blue region that we had before as, if we look here, as the union of 1, 2, 3, 4 cuboids. Okay, they are generalized cuboids. One of them, this one is infinite in the horizontal direction, but only going to the right, and infinite in the vertical direction, but going both up and down. And likewise, this one is bi-infinite in the vertical direction and semi-infinite in the horizontal direction, and these other 2 which are only semi-infinite in the vertical direction. So in general, this will be true. We can take complements of cuboids and they will be written as disjoint union of cuboids and so on. So if we define A as the class of sets which are given by the union of finitely many disjoint cuboids, then it is an algebra. In particular, we don't really need to ask them to be disjoint because it's an algebra after all. If they're not disjoint, we can make them disjoint because there are finitely many of them. For example, how can we express the union of these 2 rectangles in this form as a union of finitely many disjoint rectangles? It is enough to take these 3 rectangles here. They are disjoint and they are cuboids, and you see that they give exactly what we had before, the union of these 2 non-disjoint rectangles. So here we have them written in a disjoint way. Of course, these 2 points here, they are the same. This is just for the purpose of making the picture, so that this segment here, it does not belong to this rectangle, it does belong to this rectangle, and so on. Now we are ready to define the pre-measure. So on the algebra that we just discussed, let us start defining the measure of finite cuboids. So of course we'll define it in the obvious way. Here we have no choice. And for infinite cuboids, we define the measure to be plus infinity. Then, for every set A in the algebra that we just discussed before, we can write A as a disjoint union of cuboids, E1 up to Ek, and then we define simply the measure of A to be the sum of the measure of each of these cuboids. This is, it turns out, this is well defined, even if we can write A as a disjoint union of cuboids in more than one way. It does not matter. Every possible way of writing A like this, like disjoint union of cuboids, we'll get the same number here. So this is a well-defined. And a lemma, we will omit the proof of this lemma, is that this measure, M, this finitely additive measure that we define on that algebra, it turns out that it is a pre-measure from which we can apply Kara-Theodori extension theorem and conclude the existence and uniqueness of the Lebesgue measure on the space Rd with the sigma algebra, the Borel sets of Rd. Let us just see some examples. Here, let's consider first what is the measure of a point. We have a point on Rd and we want to show what's the measure of that point. Well, let's draw a cuboid that contains the point. We can make this cuboid have as small as we want, and the point stays here inside the cuboid. And if this cuboid has a side epsilon, then the measure of the cuboid A will be epsilon to the d. And since this point is a subset of A, the measure of the point is less than epsilon to the d. And since this is true for every epsilon, then the measure of the set that has only one point, let's denote it x, is 0. If our set A is a subspace, or the translation of a subspace, a linear subspace of our Euclidean space, in this case here Rd with d equals 2, and suppose we want to measure a set A which is a subspace. So here the set A is just a line, and we want to show what the measure of A is. If we start by some rhombus that contains a segment of A that has area epsilon, we see that the next interval of the same length as the original one, if we split it into two rhombi now instead of one, it will have area epsilon over 2, and if we keep doing this, the next one will have area epsilon over 4, and so on. And if we sum the area of all these rhombi, we get epsilon. And we can sum to the left as well, so we get epsilon over 2. In the end, we get 3 epsilon over 2. So the measure of the subspace A is bounded from above by 3 epsilon over 2. Since this is true for every epsilon, we can conclude that the measure of A actually is equal to 0.